Okay, so okay, can you see? Yes? Good. So so in the previous class we ended up with the Laplace of derivative, and I said that the Laplace of so f prime, if you remember, was s f of s minus f at time 0. Also we got Laplace of f double prime that you have in your notes. This is s squared f of s minus s at f0 and f double prime 0. So you see that it's a kind of pattern that we have here. So what's the pattern? So pattern is with the first time derivative you have one s here. Second time derivative you have s squared here. So now we can generalize this. You say if Laplace of f nth order time derivative n is gonna be, if I remember it, it is s n f of s minus Sn minus 1 means nth Sn minus 1 f at time 0 Sn minus 2 f prime at time 0 and continues to minus s f n minus 2 at time 0 minus f n minus 1 at time 0. This is general statement for the nth order of Laplace of nth order of function. So it's easy to validate this. How? Just select 2. I say 2. N is 2. So if that 2 equals to s squared f of s minus 2 minus 1 is s f of 0 minus s n minus 2 is 0, 1. So f prime of 0. Here we go. We just did for 2. Can you please close your speaker or microphone, or is all of you? So you see with the nth order derivative, you added Sn. That's right. So why I'm saying that? I'm saying derivative or differentiation with respect to time. One derivative gives you 1s. Second time derivative gives you s squared. Third time derivative gives you s squared. So this s is a representative of derivation. Are you following me, everyone? When you see s is a representation of derivation in time domain. So now I'm gonna introduce you. When I see cs derivative, we name this, when you go ahead in the course close to the end of the semester, D controller. May you heard this PID controller that I'm going to teach you in this course. We're going to write code in MATLAB to fix the system dynamics. This D is this D, derivative. Why? Because derivative gives you this. And when we go ahead, we're going to write like this, KDS. This is the controller. And we are using the controller to stabilize unstable system or to modify transient response of system, like as we are modifying suspension response of your car by the T controller. I'm going to teach you eventually how. Clear, everybody? Yes? Yeah, KD is the gain of D controller. I'm gonna introduce later. I'm just giving you now a big picture, okay? So it's a gain of the D controller. And your function as a control engineer is to tune this value, KD. You have to tune this. Means that you have to give a proper value to this, which is greater than 0. Okay? D controller. Okay. Then this is a D gain. We say gain, derivative gain tuning. Any question, guys? Now let me go and finish almost this. If you have y is equal to f of t, and its Laplace, as I told you, is L of y is f of s in frequency domain. So what's the Laplace of integration of ft dt? Here was derivative above here. Here is integration. So I'm skipping the proof because that's stupid. You can find anywhere. It's going to be f of s divided by s. Interesting to see and observe that the derivation gives you s. Integration gives you what? Gives you what? You tell me. Gives you what? What is that? Okay. 1 over s. Oh yeah. This is 1 over s in the frequency domain. So it's interesting to tell you that this integration is I part of PID controller. Integration, integration is I part of controller. So whenever you see that your controller adds this 1 over s, means that you are applying I controller. We are using I controller to remove the steady state error signal that I'm going to teach today. I previously taught you about the error signal, right, in the block diagram. So the I function, I'm going to go over that in detail, hopefully in March, mid-March, or toward end of the March. So is to remove or make the steady state value of the error signal to 0. I'm going to teach today this in the block diagram. You got it? So we write, when we go to control, your function is to tune this. We write like this, ki over s. This is gain of the I controller. You have to tune this. Exactly in the Simulink and MATLAB, you have to do that. I'm going to teach you how. Okay, because in these days nobody does it by the hands these days. It's not 60s. This is 2023. Everything is being done by Python or MATLAB or Simulink. Okay? Understood? So your function is to tune ki, gain of the I controller. So having all the frequency, the Laplace of the different function. Now let me start the block diagram eventually by this example. That we did together, that's right. And I'm saying here, oh my God. And I'm saying here is, I don't know, say tau. Yeah, tau, torque. I'm applying a force to the system. I'm applying force to the system. If you ask me what kind of force, I will give you the example of that. Because I taught you previously. The force I'm applying, I'm saying this, is omega n square, and let me put this here. Omega n square. This is a number, that's right, like this. T minus T naught. What is this, guys? I want that you tell me because I taught you a million times. Delay in which function? Look at your notes. Which input to the system I told you? This delta stands for what? Yes, delayed impulse. So it means this is our famous problem, right? That's why I told you I'm going to use it several times. Okay, and after we're going to back to the MATLAB code today or the next class, okay? So, because you have to understand this fundamentally. So, suppose that when I say delayed impulse, means this. If this is t, this gonna be delayed impulse. See? Here is t naught. That's right. You see delayed impulse. And I assume that the initial value of angle of pendulum is 0 and the initial angular velocity of the pendulum is 0. Means I'm starting from here. See here? Do you have any problem? At time 0, we are in vertical position with no motion. So for making visualized, I'm saying omega n square, and let's say delta is t minus 2. Here's t naught is 2. 2 seconds. Do you care? This is just a ridiculous example. Okay? Understand? Why I'm saying this part? Because when I go to MATLAB, I'm going to show you that when I'm applying impulse, when I get the answer, you see what's going to happen. Now I'm solving this for block diagram. I'm solving this part only. But you know the nature of the things that I'm applying is in delayed impulse. Okay, based on whatever we have here, guys, is f double prime is s squared f of s minus s f0 f prime 0. Means angle at 0, angular velocity 0. Okay, so we're gonna have, if you apply the Laplace transform for the both sides of this, you're gonna have s squared theta of s, you are transferring to the frequency domain, minus s theta at the time 0 minus theta dot at time 0, this is theta double dot, plus omega n square theta at s equals to omega n square tau of s. Everything is based on the frequency now, s, j omega. And we are not blind. This is 0, this is 0. So what you get is s squared theta of s plus omega n squared theta of s is omega n squared tau of s. Or you have the output of the system over the input of the system is omega n squared divided by s squared plus omega n squared. So now we have a by definition, we have closed loop transfer function. This is the definition of closed loop transfer function, because this is ratio of output of the system, which is the angle, over input of the system, which is the, say here is impulse. This is closed loop transfer function. After this in class, I'm writing as CLTF, will make it easy to write. Closed loop transfer function. Okay, let's plot this block diagram. Here is tau of S, input to the system, because we want to control this, that's right, at the end of the day. Not now, but later. So this is your G of S. I'm going to introduce right now. And this is the real output being compared with this. So what is G of S? We name it as open loop transfer function. This is just example of what we're going to see. Okay, the name of this is open loop transfer function. Open loop transfer function. In this course, I'm going to see OLTF. Okay, open loop transfer function of the plant, of the pendulum. So how to find this? I'm going to teach you now. But first, I have to teach you the general concept of the block diagram. First, I'm going to back to find this. Okay? Can I go ahead? Yes? Oh, sorry. This is S. Okay? In the block diagram. Okay? So, if you're done, I'm going to go and teach you the general concept of block diagram and control. Can I? Okay. I remember that I taught you once the feedback block diagram by the pendulum that you have in your notes. Now I'm going broader than that. So you have input to the system as X of S. When I say input to the system, means desirable response that you want to have. Desirable response that you want to have. Like what? Like you want to have 80 miles per hour in your car when you're driving by highway by using your cruise system. This is a control problem. You want to have 80 degree Fahrenheit in the room temperature. You want to have, I don't know, say 1 bar of 10 bar of the pressure of the water in the tank forever. Whatever. This is desirable response that you want to have from the system. Okay. Then you have a controller to the system. That in this course you're going to learn how to design it. C of S, controller. C stands for the controller. That I just introduced you DI part of that, derivative and integration. Just briefly. This controller sends a signal, U of S, control signal, to the plant, to the open loop transfer function of the plant, G of S. This plant can be your car, can be the room, can be robot, can be satellite, can be airplane, can be your body, whatever that is moving or statically that you want to control it. This is plant. Plant. This is controller. Then this plant, using this to control command, sends a real output of the system. Like I will name it Y of S. But we want to control it, so you need the feedback from the output being sensed by sensor. As I taught you previously, we name it as H of S. Output must be sensed. When you want to set the temperature of the room to 80 Fahrenheit, so by the controller that you mounted on the wall, how you know you set to 80 and you leave. After a while that you back, you see that the temperature of this 80. How it happens? Because inside the room you have a sensor. This is a sensor that is measuring instantaneously the temperature of the room. Why? Because to be compared with the desirable temperature that you want to have. So the difference between them gonna be error signal, E of S. This is error signal. The controller that I'm gonna teach you, PID controller or did lag controller by root locus that I'm gonna teach you eventually, uses these error signal to issue the control command, proper control command. And this loops continues until ESS, steady state error signal is 0. And I'm naming this signal after sensor as B of S. Okay? As B of S. So, I told you the closed loop transfer function is the ratio of the output of the system over input of the system. Y over X. We're going to find this. So, and this is, I told you, close open loop open loop transfer function. Okay, in generally, by definition, is in this general thing is B over E, the signal after sensor over E. Okay, why is that, guys? When I say open loop transfer function, means I don't want to have feedback, so I'm cutting the system from here and only feed forward. This is feedback, that's right. See, this is feedback, guys. This is feedback going and circulating. Now I'm saying another term, feed forward path. Feed forward path. So only feed forward if you cut from here and this signal doesn't go here. Is this path, guys, right? Is this. And it stops here. Yes or no? Huh? Yes? So you see that B over E is, but before that, let me teach you some rules in the block diagram. If you have this, A, B, Z, and here is X, Y. This is how we deal with the block diagram. X over Y is multiplication of A, B, C to Z. or y equals to x in a, b, c to z. Clear, guys? Yes? So yes. Now when I cut from here, this is only feed forward path, not going inside this circle, okay? What is b over e based on whatever I taught here? Gonna be multiplication of what? Just compare this with this feed forward path. Gonna be c, g, h, right? Understand, everybody? I'm just multiplying the blocks. Clear? Good. So this is open loop transfer function of this general block diagram. Okay? I'm going to simplify later. I'm just giving you the whole picture. Now when I calculate this, y over x, so closed loop transfer function. Guys, when I say closed loop transfer function, means you have feedback. Okay, let's do this. Let me delete this. Delete this. Okay. Guys, this is from high school. Look at this circle. E of s, error signal. Oh. Error signal is, let me change the color. Error signal is what? Just do this. X of s minus, you tell me what? Minus B of s. Relation number 1. B of s, okay? B of s over E of s, which is open loop transfer function, is how much? C, G, H. Yes or no? Huh? Yes? Okay. So, and what is relation number 2? What is between Y of s and E of s? You tell me. Y over E. What is that? Look at here. In this feed forward path. Yes, C, G. That's right. So from here, you see that Y is equal to C, G, E. Understand, everybody? Now, no magic. I'm putting E from here. So you're gonna be C, G. I'm dropping S because we know the S domain. Minus B. Now I'm putting this B from here to here. Sorry. Understand? Yes. So your B is C, G, X minus again C. Oh, something is wrong. Hold on, guys. He is oh yeah, sorry guys. I'm not putting the B from here. I see that because I'm teaching from my mind. So B is simply, look at here guys. Now let me go back to the sensor because I didn't teach you, that's why. B is, to change the color. Guys, only now look at this path. So what is the relation between B and Y? B and Y. B over Y. B over Y. What is that? Yes, H. So I mean that output of the sensor over the input of the sensor. So I'm gonna put B from here. Okay, B. So it's gonna be X minus B. B is Y H. There we go. So Y equals to, at the end, CG X minus YH. If you are done, I will go to next page. Can I go to next page? Okay. So Y, based on what we derived, was CG X minus what? YH. YH. Or it is CGX minus CGHY. If I move this to the left hand side and the factor out of the Y gonna be CGH CGX. So the closed loop transfer function, which is output over input, okay? And you have to know and eventually memorize. I'm going to teach you how. Is CG divided by 1 plus CGH. Bingo. Numerator, don't write, just listen to me very carefully. Numerator is the block multiplication of block diagram in feed-forward path, CG. Here 1 plus CGH, multiplication of the block diagram in feedback path, CGH. See what I'm saying? Yes? This is feed forward, this path. This is feedback path. And no need to mention you that this is controller plant transfer function sensor transfer function, sensor transfer function. So we got it. I'm writing here closed loop transfer function by having sensor in the loop, by having control in the loop, is CG 1 plus CGH. Open loop transfer function gonna be CGH. Keep this in mind because I'm gonna work on this, guys. This term. Oh, okay. So the numerator of the closed loop transfer function, CG, is the multiplication of the blocks in the feed forward path here. See, everything is going forward, right? CG, right? And denominator, this term is 1 plus this term is the multiplication of the block diagram in feedback. See, this is feedback. CGH. Understand? Everybody? Good. So, but there is a big but. I didn't teach you the controller yet. So, based on my own right, because I'm a professor, I can't do that. I'm going to say bye-bye to the controller for now. For now. Okay, until March, mid-March probably. And Guys, if sensor of your home receives signal in the format of temperature, transfer and readable for your system, and send exactly the same amount outside, okay, what's this ratio gonna be? Sensor receive Y and exactly sends in the digital format outside. What's the ratio of the B over Y? I'm saying B exactly is Y. On the other hand, what's that ratio? 1. So if your H sensor transfer function is 1, we name it technically ideal sensor. Ideal sensor. In this course, for sake of teaching, we assume that our sensors are ideal. Maybe in reality, some sensors, they are sending out only 98% of the measures, okay? Because of dust, because of, I don't know, bad locations, whatever, beside of malfunction in internal circuits, okay? But here we assume that H is 1, we are using ideal. If I use that, I'm gonna say also by 2 for now, or H of S. So I'm simplifying everything to this for now. Input, there is no controller yet because I didn't teach you. G, plant, which is for our example, this example that I'm gonna back here, this example, pendulum. Output, sensor is ideal, I'm removing that. Feedback. When I remove the sensor, we replace with 1, that's right? Yes? We change the name of this block diagram. We say unity 1. Feedback block diagram, BD, block diagram. Unity feedback block diagram. When you hear that unity feedback in industry, means that your sensor is ideal, is perfect, or Italian says perfecto. Okay? Clear? Yes? Guys? Now, being said, to go back to our problem, now you know that closed loop transfer function, because I said there is no controller yet. H is 1. There is no controller yet. Gonna be G1 plus G, closed loop transfer function. And open loop transfer function of your plant, there is no controller yet. H is ideal. So open loop transfer function gonna be only G. Here we go. Plant. Clear? Everybody? Now, this is, let me delete this because this is going to be confusing. This is exactly what I plotted here. Do you see the G here? Yes? And this is unity feedback. Why? Do you see sensor here? No, we don't see it. So now you have output over input. Output over input, which is this closed loop transfer function. So to find put it here, you have to first find G. From where? From here. Bingo. Bingo. Understood? Yes? I'm going to do that for you. Okay? If you are done, I'm going to go to the next page and find the G, open loop transfer function. Okay? So, I said that output or input, this is just example, okay, is omega n square s square plus omega n square. And this is equal to, because this is closed transfer function, G1 plus G. And the G here is based on what I taught exactly today, is open loop transfer function to be replaced here. To be replaced here. As I'm going to do exactly in the Simulink in MATLAB. So it's now this is kindergarten. This is omega n square 1 plus G is equal to G s square plus omega n square. Omega n square plus G omega n square is G s square plus omega n square. If you do that, I'm just skipping, please do at home. Gonna be omega n square divided by s square. There we go. This is number, natural frequency of pendulum. And this is s square. Guys, I want that you do the brainstorming. And you let me know, I just taught you what this reminds you guys. What this reminds you. You tell me. I just taught you. Let me go to the page I taught you. What is this? What is this? Yes. I controller, yes? Huh? So you have 1 over s squared. I'm just giving you hints from now. This is very early. Means that you have 2i. Technically, we say your system has by itself 2i in open loop transfer function. Means that your system intrinsically has 2i controller inside. When you're designing PID controller later with me, you don't need I for this system because already has it. See what I'm saying? Yes? See what I'm saying? So you see that, oh, pendulum without friction at the hinge joint has I inside already. I controller. Interesting, right? Okay. So now we're gonna put here tau plus minus, and always, as we're gonna do in the Simulink, always here you're gonna put open loop transfer function. For this problem is omega square or s square, and real output to be compared with the input. Okay. So this generates error signal, E of S. Now your function is, as a control engineer, guys, to make a steady state error signal to 0. You say steady state. Why we say because when you run a dynamical system, and if this is the error signal, if you plot it, okay, it must be like this. Here is transient, we name it transient, means vanishing. Transient response, transient. But here is steady state. You want to make steady state error signal goes to 0. Means the output follows the behavior of the input. Because E here, this is just a stupid example, okay, is tau minus theta. Tau is not torque, it's just excitation here, the system. Don't confuse with the torque, because you cannot subtract torque from angle. See what I'm saying? You want to make this 0. This is your function as controlling 0, one of your functions. So I'm going to stop it here, but the next class, I'm going to teach you how to calculate this and calculate this. I have many things to talk, and then we're going to go to the MATLAB again. Okay? Understand? So in the next class, I'm going to teach you about the final value theorem that leads us to calculate this in time domain. Okay? Everybody? Any questions? Any questions? So again, I'm overemphasizing. If you see a open loop transfer function after graduating working industry has one S in the denominator, you go, oh, system by itself has an integrator. It shows that you have vision. See what I'm saying? You are not blindfolded control engineer. So, oh, system by itself. We don't need I probably. We just have to design PD control. See what I'm saying? Yes? Right, guys. So see you next week, and enjoy your weekend. Thank you. Thank you.